Yeah, hello. So I'm going to talk a bit. Can you hear me okay? Microphones are good? Okay, yeah. So today I'm going to talk a bit about search. It's nice to be back in Bloomberg because I did work here originally about 3 years ago. So yeah, who am I? If my thing will work. Who am I? I'm Eddie. I run the data science team. There's about 8 of us at the moment, if you include interns, and the sort of things we're interested in are search and recommendations, analytics, all sorts of classification problems centered around fashion data. So who is Lyst, if you don't know us? We're basically like a fashion aggregator. We scrape the web, we collect loads of information about fashion products, and then we sell them to our end users. So our business model is essentially taking this stream of semi-structured fashion data and turning it into structured data so we can present it to the users and sell them clothes, basically. So a couple of little stats about us. We scrape about somewhere around 4 million items every single day, and that's about 50K new products each day we get on site. So the thing we really have to watch out for when we're doing anything with data is we need to automate everything because we get so many new products you can't really use people to do anything with them. For example, a lot of high-end fashion retailers would manually write descriptions or manually say this product is blue, but we can't do any of that. We have to do it all with machine learning instead. Okay, so search. So like I said, we scrape all our data. Searching that scraped data is really critical to us. We use our search algorithm for all our ads as well, and our ads is basically how we make money. So the search algorithm needs to be very good, but we don't have control over the data, so we need very robust algorithms that can handle these heterogeneous data. So I think search is quite hard for a number of reasons. If you think of a lot of data science projects, you have things like recommendation, and in recommendation you're mapping some finite set of objects to another finite set of objects. So you might be recommending products based on products, or you might be recommending products based on users, for example. So you've got these finite maps. Or if you think of a classification task, you're generally mapping to some very small finite set of categories, like it could be, I don't know, is it a cat or a dog? You're just mapping to 2 categories. I think search is especially hard because you've got an infinite set of strings and you're trying to map that to a finite set of categories. So the input is very broad. I think also is this problem around expectations. Google has ruined search for the rest of us. Like, no matter how good your search is, it's never going to be as good as Google. Google have made like the magical and everyday experience, and you've got to try and compete with that, which is quite hard. And the main problem with search is like, what is a good result? What is relevant? You need to try and understand this, and the only way to really understand it is through users. You can't perform a search and look at the results and say, well, these are the best results. You really need to look at users' interactions to understand that. Okay, so what we really care about with search is precision and recall. I'm sure you're mostly familiar with this concept. I've got this nice diagram. So precision is essentially, out of all the results we return for search, how many are good? And recall is how many selects are relevant? Ah, right, okay. Our designer made this slide, and he's actually put the same copy for both precision and recall. Yeah, okay, should have checked that. But yeah, so basically recall is how many good results you return out of all good results. Precision is, okay, let's skip this one. Okay. Yeah, I always get confused. True negatives, false negatives. They're sometimes hard to remember. But look it up on Wikipedia if it's important. Okay, so let's talk about the way that search is normally done. So thank you. So there's this thing called BM25 from the 80s, I believe, and that's more or less what most out-of-the-box search solutions are using now. Essentially, you look at the frequency you look at the terms in your search query, you look at the terms in all your documents you're trying to match, and and then you look at the frequency of those terms, essentially. So it's based on TF-IDF, which is another acronym I can never remember. I just say T and Fs until it sort of sounds right. But TF-IDF, term frequency, inverse document frequency. So for example, if your query contains a lot of your documents are going to contain the also, so it ranks that phrase downwards because every single document might contain it, so we know it's not important. Whereas if we had a term like Superman, that's going to be in very few documents, so those documents which Superman is in should be relevant to your search query. So the problem with this approach is that it's lexical, so you're just basically doing string matching on symbols. You're saying, well, this symbol's here, so it's probably relevant. I think we've seen from the history of AI that these sort of approaches don't really work. They're not scalable because it's just rule and symbol based. We're trying to move away from that into like more semantic type approaches that you're seeing in deep learning. So let me show you a couple of things that go wrong with this simple lexical approach. So here I've got a search for little black dress, and as humans, even if we're not fashion people, I think we know the little black dress is like a fashion unit. It's like a multi-word expression particular to fashion. It's a small cocktail dress or a short cocktail dress, something like that. But if you just use a lexical approach and look at the individual symbols, you don't get the right results. So you can see here that the first three results for little black dress are actually matching a designer called Little Mistress, which isn't really the user intention. But in this algorithm, we're saying, well, the designer of a product is very important, so let's rank designer matches very high. And here, matching the designer is the incorrect move. Likewise, here's another example. So the user's searching for red Valentino, and we're getting red products that are by Valentino, which sounds like it's correct. But the problem is that Valentino have a sub-brand called Red Valentino, which is a different designer, and the user could also be searching for that. So these simple methods of just string matching don't really work. We need to know more about the user intention behind the search. And here's another little one that's not strictly related, but if I showed you this, I mean, what would you think that was? I mean, like a password, a random string. This is actually a designer, BCB Max Zaria, which I think the first time I saw this, I thought, oh, autocomplete was broken. But this is a real designer. And people actually refer to this, oh yeah, they don't type it all out, they refer to it as BCBG. And likewise, there's designers like Saint Laurent, where people refer to them as YSL, not the full word, which is good because I can't spell Saint Laurent. But this is another thing we need to think about in search. There's ambiguities, people shorten things, there's nicknames that people use. We need to know all this, and simple string matching won't achieve that. Okay, one more example. So here's 3 products. This one is a dress. I think we're all aware of that. What do you think the second product is? Any ideas? Bag? Sorry, the top product. So it's actually a dress shirt because it's a formal shirt. Anyone guess what the third one is? So we've got a dress shirt, and a shirt dress. And this is a real product. People search for this, and well, they tried to search for this, but our current search doesn't really work very well for shirt dress. We just get shirts and dresses, not shirt dresses. So again, order matters, and if you use something like bag of words, where you get rid of order, which is most search algorithms, it doesn't, you get, this breaks. Okay, so what is a good result? What is relevancy in search? It's, like I said, it's quite hard to determine, and most search algorithms aren't supervised in any way, so it involves a lot of tuning of parameters and sort of looking at the results and going, oh, well, this looks all right. So what you really need to do search properly is get some labels. You need to know what is relevant for a given term, but that's quite tricky because we have an infinite number of terms. So how do we get labels? There's a couple of ways. The first and easiest is click-through data. Click-through data is basically someone's on the site, they search for dress, they click on a dress, so we assume that's a positive signal that they search for dress and this product is a good example of that. There's a few problems with click-through data. Well, it's easy to collect, that's a good advantage. It's free, users are browsing the site, we get loads of click-through data. But there's a number of problems with it. For instance, we don't get any negative data, so if a user searches for something and doesn't click anything, we've got no signals as to what is a good product for that search term. And likewise, we've got no idea about degrees of relevancy. So if you search for dress and click on 10 products, we've got no idea which of those 10 products is the most dressy out of the clicks. And also, we don't get any negative signals. So for negative signals, we sort of have to make some assumptions about that if a user didn't click a product, then we assume it's not relevant, but that might not be the case. So the other way to get good labels is with crowdsourcing. I could probably do a whole presentation on crowdsourcing because it's a really interesting area because the people that you use are actually quite unreliable. So you've got to set up your crowdsourcing in a way that combats that unreliability. For instance, one thing we found is that if you pay a person 3 pence to do one item, you still get you still get bad results. You get better results if you pay 3 people 1 pence and take that average, and then it works out better than paying one person more. But the problem is, so given a search phrase results, how can we actually label those results? So here's one way we could do it. We could use an ordinal scale and say, here's a search phrase, light pink heels. Please rank the following products from 1 to 5 in terms of how relevant they are to the search phrase. But this doesn't work very well because it's very hard to rank in the middle of a scale. Like 1 is very easy, it absolutely doesn't match. 5 is very easy, like it absolutely matches as a perfect example. But out of these products here, what rank would you give them? They're all sort of pink heels, but they're perhaps not perfectly pink heels. Like one's a wedge, one's multicolored. What rank do you actually give those? So instead, we use this pairwise comparison technique that we got from a paper called Hipster Wars. It's a really good paper if you want to have a look at it. So the user searches for blue trainers. We show them 2 products. One, I'd say the one on that is more blue is a better example than the one that has orange. So then the user can say, oh, well, the blue one is better. And that's an easier decision for the crowdsourced moderator. And then we can take all those binary decisions and use something called TrueSkill to translate them into a rank of which product is best for a given search phrase. So for every product, we represent it with a normal distribution. Then we pair up products, and the product the user clicks, we update the parameters of the distribution, and the variance gets lower, the mean goes higher, and we keep doing this multiple times until we build up a complete ranking of all products. And the rank is basically the mean of the distribution minus something times the variance, and the higher you multiply the variance, the more that you're saying you're penalizing the rank based on the unknown variance. So we do that lots of times for many search phrases, and then we have rankings for every search phrase, and we can train a model. So the way that we pick the search phrases is we just looked at all our search phrases and sort of did a greedy algorithm to replace the terms in the search phrases with like what we call templates. So you can see here that the most popular search is designer plus category, which is basically like Hermes sandals or Gucci dress. That's what most users are searching for. We built a list of, say, 20 of these templates, sampled search phrases from all the templates, sampled products from all the search phrases, and then did crowdsourcing on them. And the way that we sample products is we use existing rank in our search, which is just BM25, and sample products from percentiles in the results so that we have bad products and good products, and then the users will the moderators will re-rank them for us. And we found that re-ranking actually works, so we could see products that are initially at the bottom of our results got moved to the top, and products that are at the top got moved to the bottom by the moderators. So now we've got some data on what is relevant. How can we use that to make a better search algorithm? So here's a model, again from Microsoft. This is like a deep neural network. And what we do is put in a query into this neural network and some products or documents. And one of the products is relevant to the search query as predicted by our crowdsourcing, and some products are not. And the idea is that the model will maximize the probability that the relevant document will be returned for the query, and the unrelevant documents won't. And that's how it works, basically. And one of the nice little tricks they use for this is something called trigram hashing. So instead of using bag of words or massive vectors, we just look at all the trigram frequencies in the documents and phrases, and it reduces the dimensionality of the input, which is nice. And it gives us some nice things like morphologic invariance. So you might have something like, I don't know, dress and dresses, but they both contain the same trigram internally, so we get round having to worry about pluralization and that sort of thing. And it also helps out of vocabulary problems. So instead of saying each word is, we have a coefficient for each word, we just do trigrams. So once we get unseen words, we can decompose them into their trigrams and we know something about them rather than not knowing anything about them. So this is a simple model. And then we're actually working with a deep learning researcher who worked on this model, and this is updates the DSSM to have a convolutional max pooling layer. And what this gives us, well, the max pooling layer basically lets us drop unimportant features, which is really valuable. So say, like the word the isn't very useful. We don't really need to know about that trigram usually. So max pooling will drop that from our feature set for us. And the convolutional layer basically gives us like supervised contextual feature detectors. And from his paper, it shows the results are better than not using convolutional layers. So here's some results. These aren't our results. These are actually from the paper. We haven't quite finished implementing this yet. So you search for Microsoft Office, and you can see that the top ranked results are all related to Microsoft Office, whereas the bottom ranked results are related to things like physical offices. So the representation that we're learning in this model, has a semantic power to distinguish between the meaning of words, depending on the context they occur in. And the same for car body shop. The first hit is car body kit, which sounds good. And the bottom hit is force field body armor. Don't know who was searching for that, but so it does what we want it to do. I'll just talk a little bit about how we actually deploy this thing. So to actually do the search quickly, we pre-calculate all the representations for every product. We just take the hidden layer of our model, store it in a Postgres database, and then we have a little C module that does very fast searching over that, over those representations using artificial neural networks. Previously to this, used Elasticsearch, and our queries were taking like 500 milliseconds to a second to answer, which is way too slow for search. And using this method with Postgres, we're doing it in about 50 milliseconds. And we started using this for basically all our machine learning infrastructure at Lyst. So there's something else we can do with our deep learning model. We can try to include images, which will give us a lot more power. So for example, with the little black dress example, many products won't say, I am a little black dress. But if a few products do, and those products have images that are similar to other products, we can start matching more and more by using the image information. So we trained another deep convolutional network based on AlexNet. It's 8 layers deep. It has about 60 million parameters. We trained this on a big GPU server. And the nice thing that we do is we have lots of fields we're interested in. We're interested in things like gender and color and category and all these properties of a fashion product. So we want to build an image representation that can represent all these different fields. So We optimize the network for predicting color. Then we basically swap out part of the network, keep the representation, and then optimize for type or something like that. And then we build up this robust representation that knows about all the properties of products that we're interested in. Yeah, and it takes absolutely ages. It's about 6 hours per iteration this takes to train, and it needs about 30 iterations. Yeah, so this is it working. So we put in an image. And it predicts the color, the gender, what we call the type and category. It actually gets it slightly wrong here. It says it's a 3-piece suit when it's a 2-piece suit, but we have very few suits on Lyst, so it's not the best example to show. But you can see that it mostly predicts everything correctly, so we can say our representation is quite good. Yeah, so on gender and color, it gets something like 90 to 99% accuracy, whereas on the category, it's about 85% accurate. Yeah. So another thing we did with this representation, just have a look at if it is good. We take the representation and reduce the dimensionality to 2 dimensions so we can plot it. And what you see here is a random selection of products in 2 dimensions based on the representation that we've learned in the convolutional neural network. And it's got some interesting little properties. So if we zoom in, you can see that it sort of clusters all the shirts together. This is like a little shirt peninsula in the representation space. So it is learning about similarity between the images. We go somewhere else. You can see there's sort of a little shoe island there, and there's some model shots. And if you play about, you can see it's roughly classifying the right thing. You get color groups, you get pictures with models in, you get pictures with shoes, picture on the side or from the top, and it does seem to be understanding what we need. So the next step for us is to incorporate this into our current search model along with the textual search, and then hopefully we'll have a world-class search. So thank you. So in conclusion, search is fun, but it's very hard, and I think it's a topic that people aren't looking at as much as other topics, such as recommendations. So I think as a community, we should start talking about it a bit more. Thanks.